Hello, welcome everyone. In today's lecture, we are going to look at a new concept, which is finding out the effective stiffness of beams. Okay. So by the end of the lecture, what you'll be able to do is determine the effective stiffness of different types of beams. And the point of doing this is so that we can analyze the vibrations of such beams. Okay, and that we'll do a couple of lectures later, but in this class, we'll just focus on how to find out the effective stiffness of beams. Okay. So the first question that you have to ask is, why do we need to calculate effective stiffness of beams? The reason is beams are continuous systems, or in some sense you can call them infinite degree of freedom systems. Okay. So if you want to analyze the vibrations of beams, essentially we need to reduce them to a discrete spring mass damper system. So because that is the one that you have learned in this class, how to analyze them. So the last few lectures we looked at the single degree of freedom systems and what is the response in free vibration, in forced vibration, and so on, right? So essentially what we are trying to do is we are trying to take a continuous system like a beam and then turn it into a discrete system so that we can analyze them in the same framework that we have been talking about for the last 2 or 3 lectures. Okay, what do I mean by continuous system? So let's say if you think about the spring mass damper, that system that we looked at, we essentially have a spring with a spring constant K, a damper with a damping coefficient C, and then you had a mass M. Okay, and it is constrained to move in the direction X. Okay, so here you have a discrete mass, a discrete spring, and a discrete damper. Okay, and the motion is defined with respect to that of the mass in the X direction. Now, if you think of a beam, say let's think of something like a cantilever beam, which is probably the simplest to look at, right? Say you have a cantilever beam, okay, and then you vibrate this beam. So how do you vibrate it? One way you can do it is you can apply a force initially, okay, and then displace this beam from its initial position and then let it kind of deform by some amount delta, okay, and then once it deforms by this amount delta, you can take off this force. So then what would happen is that this cantilever would go that way, right? So essentially it will kind of keep oscillating from one position to the other. Okay, so essentially it is going to undergo vibrations. Okay, now if you think about this cantilever, what is the stiffness of this cantilever? Okay, so what is this K for this cantilever? Okay, so what is the mass for this cantilever? Okay, and what is the damper or damping constant for this cantilever? It is not so clear, right? And the reason it is not so clear is because if you look at this cantilever, even as it vibrates, say it takes a shape like this. Okay, now if you look at this shape, if you look at a point here, the displacement of that point is say delta 1. Okay. On the other hand, if you look at a point here, the deflection of that point is something else, delta 2. Okay. Now, what do you call as the deformation of this beam? Or what do you call as the displacement of this beam? Okay. If you say it is delta 1, then this part of the beam here is not moving by the same amount, unlike this mass here, where the entire mass is moving by a distance x, right? So if you think about this beam, every point in the beam along its length basically has a different displacement, okay? So this x is not one number or one variable, but essentially is composed of an infinite number of variables, okay? The same thing now you can think about the stiffness, okay? What do you mean by the stiffness of a beam? Okay, you can say stiffness is some force divided by some displacement. Okay. Now, if I apply a force here at the tip of the beam, it displaces by some delta. Okay. Now I can say that this K of this beam is F over delta. Okay. Now, if I take the same force, but now I apply the force somewhere else, the displacement at that point is going to be some delta 1. It is not going to be delta. Okay. Now, can I then say that my K of this beam is F over delta 1? Okay, which is correct? Is it F over delta or is it F over delta 1? Okay, so there is a conundrum here. So when you have a continuous system, right, where the mass is distributed over a spatial area or some spatial length, then it's hard to define what the mass of the system is. And it is also somewhat hard to define what the stiffness of the system is. So if you don't know the mass and if you don't know the stiffness, how are you going to analyze its vibrations, especially using the single degree of freedom system framework that you have seen so far? Okay? So that is why we have to look at, or we have to calculate, what is the effective mass and effective stiffness of these beams. Okay? So that is what we are going to do now. Okay. Now, from what I told you already, it is clear that this effective stiffness of a beam is not some universal parameter. Okay? Depending on where you apply the force and in what direction you apply the force, the stiffness changes. So the first thing you must keep in mind is that the effective stiffness, K effective, depends on the specific location on the beam in which at which the force is applied, and it also depends on the direction in which the force is applied. Okay? A simple way to kind of think about this is, say suppose you have a cantilever beam like this. Okay? And then let's say the cantilever has a rectangular cross section. Okay? Now, if you apply a force on this cantilever in this direction, say Fx, for example, then the cantilever will deform by a certain amount. On the other hand, if you apply the same force, the same magnitude of force, Fy, that is equal to F, and this is also equal to F, the amount of deflection you are going to get in the y direction is going to be much smaller than the amount of deflection you are going to get in the x direction, because the moment of inertia about the y-axis is much smaller than the moment of inertia about the x-axis. Okay? So essentially, if you apply the same force F in the x direction on this beam, then the amount of deflection you're going to get is much larger than the deflection that you're going to get if you apply the same force F in the y direction. So even with this simple example of a cantilever beam, you see that depending on which direction in which you apply the force, the amount of deflection is going to be different, which means that the stiffness is going to be different. Okay? And you can also easily see that instead of applying the force at the tip of the cantilever as you have done here, say you apply the force at some point in the middle, then the amount of deflection you are going to get is also going to be smaller. Okay? So if you think of the effective stiffness as force by some displacement, then the effective stiffness is going to be larger if you apply the force at some point in the middle of the beam rather than at the tip of the beam. Okay? So that is the reason why this effective stiffness is always defined with respect to a specific location and with respect to a specific direction in which the force is applied. Okay? Now, having said that, we can still look at specific cases of effective stiffnesses. Okay? So in this case, we have a cantilever that is subjected to a force P at the tip. Okay? You can find out then when you apply a force P at the tip of this cantilever, the deflection of this cantilever is going to be PL cube over 3EI, where E is the Young's modulus and I is the relevant moment of inertia. Okay? You can actually calculate this displacement using Castigliano's method that we have learned in this class, or you can also look at tables that you probably have in a mechanics of materials textbook, which essentially lists formulas for this kind of deflections for different loading conditions. Okay? So anyway, the deflection for this particular cantilever, if you apply a force P at the tip, is going to be PL cube over 3EI. So in that case, you can define the effective stiffness of this cantilever for this particular loading configuration as P over delta, and that turns out to be 3EI over L cube. Okay? Now you can say that the deflection or the effective stiffness of the cantilever beam for tip loading is 3EI over L cube. Okay? Now, this effective stiffness is sometimes also called as an equivalent stiffness. Okay? So these terms are often used interchangeably. Okay? Now, in this case, I told you that you can essentially find out the effective stiffness as a force over displacement. you can also find out the effective stiffness by a different method, which is essentially taking the strain energy of the system and equating it to half K effective delta square. Okay, so it is nothing but, if you think of a spring, the potential energy stored in the spring is half Kx square. Okay, and that essentially, in some sense, is the strain energy stored in the structure. So essentially, you can take the displacement at the point where you are defining the effective stiffness, essentially multiply the displacement or square the displacement, and then multiply by K effective times half, and you can equate that to the total strain energy that is stored in the structure because of this deflection. And by that method also, you can calculate what delta is. Okay, both of them are actually exactly equivalent to each other. Essentially taking K effective as force over displacement, or taking half K effective times delta squared to be the strain energy, will essentially give you the same value for K effective. Okay, so this is a very simple case of a cantilever that is loaded at the tip. Okay, now let's start looking at a little bit more complicated cases. Okay, so now let's think of a simply supported beam like this. Okay, that is subjected to a force P at the middle. Okay, this force P again is subjected at the middle of the beam, not somewhere else. Now you can find out that in this case, the displacement at the middle of the beam is going to be PL cube over 48 EI. Okay, again, this is something that you can derive using energy methods or Castigliano's theorem, or you can look it up in appendices in your mechanics of material textbook. Okay, now we again define K effective the same way. The force that we are applying is P, and the deflection that we are getting is PL cube over 48 EI, and the effective stiffness essentially turns out to be 48 EI over L cube. Okay, one thing that you should notice here is that the effective stiffness does not depend on P. Okay, the effective stiffness depends only on the geometry of the structure, the loading conditions, and the material properties. Okay, so the geometry here comes in the form of I, which is the cross-sectional area, which is the moment of inertia, so that is related to the cross-sectional area, and then E is the Young's modulus, and L is the length of the beam. Okay, so the K effective depends only on the geometry of the structure and the material properties of the structure. It doesn't depend on the force that you're applying. Okay, so that is your K effective. Now, if you take this same beam, but instead of applying the force at the middle, say you apply a force here, then the deflection of the beam might kind of look like this. Okay, now in that case, the maximum deflection may not actually occur at the point where you're applying the force. Okay, now if you now calculate P over delta, okay, let me call this P1 and say delta 1, P1 over delta 1, that is most likely not going to be equal to 48 EI over L cube. Okay, in fact, it won't be. It will be a different value, and that depends on what exactly this location is. Okay, so again, you are applying the same kind of force, essentially a force in the downward direction. Okay, it's the same beam. It is just that you're applying the force at a different location, and what you find is that the effective stiffness for that particular loading condition is different from the case where when you apply the force at the middle. Okay, so this is something that is very important. Even though it might be the same beam, the effective stiffness, how you define it, depends on at what location you're applying the force. Okay, you can extend this concept to somewhat more complicated beams. So here you have an L-shaped beam. Okay, and we have again looked at examples like this in the previous lectures. And now if I apply a force Fy in the vertical direction, and this L-shaped beam ABC is in the XZ plane, then it is going to deflect by some amount delta y. Okay, you can now define the K of the beam for this particular loading configuration as Fy over delta y. Okay, so this is going to be some numerical value. Again, that depends on the lengths L1 and L2, the cross-sectional area, the moment of inertia, and the material properties, especially the Young's modulus and shear modulus of this L-shaped beam. Now, if you take the same beam, okay, and now if you apply a force say in the x direction, you will get some deflection delta x. Okay, you can be pretty sure that this fx by delta x will not be equal to fy divided by delta y in most cases. Okay, again, what it's telling you is that the deflection or the stiffness is defined with respect to a particular point and a particular direction. So the stiffness of the structure in the y direction is different from the stiffness of the structure in the x direction. And you can start to see why that is the case, because when you apply an Fy, you are going to have bending in this segment CB and bending and torsion in this segment AB. Okay. On the other hand, if you apply an Fx, you are going to have bending in CB, but you are going to have only bending and axial deformation, not torsional deformation in AB. So effectively, the mode of deformation itself changes when you go from Fy to Fx. So the stiffness of the structure is also going to change. Okay? So, but still, with all these caveats, it's still useful to define what is an effective stiffness for a structure, because in most cases, you're going to have either an Fx or an Fy, and then we can analyze the vibrations of this structure for forces that are applied in the y direction or the x direction and so on. Okay, so that is why we still come up with this concept of effective stiffness. Okay, so in the next lecture, we will try to look at how we can define the effective mass of a structure. So if you go back, we essentially have taken a continuous system like a beam and effectively replaced this k by some k effective. Okay, now in the next lecture, what we're going to do is we're going to take a beam and then replace this mass, a discrete mass, by some m effective. Okay, and once we know m effective and k effective, we can usually find out c experimentally, and then that defines all the parameters of the system, and then you can analyze the vibrations using the single degree of freedom system framework. Okay, so that is what we'll do in the next lecture. Thank you.